Hello and welcome to IEEE Soft Robotics Podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks. Hello and welcome to IEEE Soft Robotics Podcast. Hello, Professor Sergey. Thanks so much for joining us on the podcast. Such an honor to have you.
Thank you for inviting me.
So I'd like to ask you first how you'd like to define yourself for the audience who may be first time listening to you. How would like to define yourself?
Sure. I'm a computer science professor at UC Berkeley, and I work on algorithms for machine learning and reinforcement learning with a focus on embodied learning systems. So these are learning systems that are designed to control robots or other machines that are situated in the world, that take actions that affect the world around them and that reason about the long-term consequences of their actions. And to me, the goal of studying these problems is really to give us a particular lens on the question, on the big questions in artificial intelligence, because I think that to really tackle those questions effectively, we need to be thinking about machines that are situated in the world in much the same way that we are.
So I'm going to ask you about your childhood. We ask each guest about their childhood. How was your childhood was that makes you motivated to do what you do? I don't know if you have any memories about your childhood.
Well, yeah, I don't know how much I can say that connects this meaningfully about my childhood. It's something I could say that maybe that's in the spirit of this question is maybe a little bit later when I was in college. Initially the thing that I had actually wanted to study and to work on as a career was not artificial intelligence. It was actually computer graphics, and the part of why I was interested in computer graphics was this is maybe not that unusual for at a particular age. I wanted to work on designing video games. Like this was the thing that I wanted to do, and I was pretty good at certain things, at programming, at designing 3D models, art, things like that. And this was something that I was very enthusiastic about. But the more I got into it, I actually did an internship at a company that made video games. I started working on when I started my PhD, I was working on technologies and computer graphics. The more I got into it, the more I realized that the big questions in that area really concern themselves with simulating or emulating aspects of the real world. And one of the most complex and most difficult aspects of the real world to simulate is the behavior of intelligent agents, the human mind, which, of course, really leads into the problem of artificial intelligence much more so than the problems in computer graphics. So, my own path towards this problem actually came at it from the standpoint of how do we simulate what happens in the real world.
Mm-hmm. Great. So because let's give a step about when you mentioned that question about how to simulate what we already have in evolution, for example, the brain. And we ask about the relation between the robots that design the hardware and also the side of the brain side. So how do you see the correlation when it comes to robotics? Do you think which parts really need more focus, do you believe, from the experience you have?
Yeah, it's an interesting question. My own perspective on it is that, if we want to design robots that actually solve, real meaningful problems that we need solved in the world, we obviously need to think about both sides of that equation, right? We need robots that are physically capable of doing the things we need them to do, that are robust, reliable, safe, and also endowed with a kind of, computational mechanisms that allow them to solve those problems. At the same time, if we think about the capabilities of the human mind, people are remarkably good at repurposing, peculiar physical systems to accomplish whatever they want to accomplish. So, a cute and relatively simple example is, there's this device that you can get if you need to maybe clean up your lawn or something, called a trash picker. It's a stick with a little gripper at the end. It's actually a very strange device, and it's not at all like the human hand. Of course, it's a little piece of plastic with a little metal gripper at the end and a little trigger. But a person can pick this thing up and figure out how to use it quite dexterously within just a few minutes. So whatever co-adaptation we have between our brains and our bodies, and there must be quite a lot of it because we've had our bodies for quite a long time. It seems like our minds are incredibly flexible when it comes to learning how to utilize other embodiments. And what that tells me is that the right learning-based control method ought to be able to make a lot out of whatever hardware it's provided with. That doesn't mean that we shouldn't be thinking about hardware. We definitely should. It just means that maybe we should think less about hardware as a tool to make control easier and more as whatever other constraints are placed on it, reliability, etc. And then build control algorithms that can figure out how to use whatever weird hardware we provide them with.
Mm-hmm. Right. So because of in that case, what do you think may be the hard aspect, or maybe something for you still you can't really understand how it works when it comes to learning, or maybe what's still missing, do you think, for your work, or maybe in general for learning? Yeah.
Yeah, that's a very big question. I don't know what the biggest thing is, but there is one thing that's been on my mind a lot lately that we've made a little bit of progress on, but I think it remains quite a mystery, which is that we have algorithms at this point that can learn physically complex manipulation skills, things like that, but in a lot of ways, when we observe what these algorithms do, reinforcement learning algorithms, imitation learning algorithms, they don't look the way that human learning looks. Like if you put a person in front of some weird contraption and ask them to figure out how to do something with it, they're going to try like random different things. They're going to do some amount of trial and error, but it just doesn't look the same as what a reinforcement learning algorithm does. And I think that's because humans approach problems with a great deal of kind of priors built up from their past experience. And we can throw lots of data and lots of experience at robotic systems too, but we haven't quite, I think, nailed the question of how to get them to use it effectively. How to get them to use it not just to figure out generalizable visual features or things like that, but how to figure out the right priors for acquiring new skills. That when you're asked to unlock a door with a funny door handle, that whatever you're supposed to be doing involves like fiddling with that door and not waving your arm in the air in random ways. So these are very common sense, seemingly obvious things to us, but they're surprisingly difficult to shoehorn into learning-based algorithms. How to utilize diverse prior experience to constrain the process of acquiring new skills.
Mm-hmm. And do you think that when it comes to continual learning, when we speak about this, robotics, how do you see? If you can tell more about how we can design machine learn from each other as well, and also the continual learning. And if we speak about human, they have this lifespan. So when it comes to robotics, if we speak about in the future, how do you have this kind of continual learning? How do you see that?
So I think in many ways that is very much on the track to the right problem formulation. I think that the problems we start to encounter there, it's not just formulating the process. I think it makes sense that the process ought to be something like a continual lifelong learning process. But we start running into questions like, what's the right representation to use? Like, what should you have all this prior experience of past tasks. What should you distill them into? How do you appropriately represent prior experience in a learned model so that it can be maximally useful for acquiring downstream skills? There are a few starting points. We have things like meta learning algorithms. We have Bayesian deep learning methods, things like that. So they all serve as good starting points. But I think that there are also a lot of question marks there.
Mm-hmm. And when it comes to reinforcement learning, because I think there's a paper published today about that, maybe reinforcement learning is enough for maybe the level of intelligence we issue. I don't know how do you see that this paper, for example, or maybe in general from your work, do you think reinforcement learning is enough when it comes to reaching the level of intelligence, maybe equivalent to human as well?
It's a little difficult to answer that question because asking whether reinforcement learning is enough is a little bit like asking whether optimization is enough. Like, almost any rational decision-making problem can be formulated as a reinforcement learning problem, but that doesn't mean that reinforcement learning methods can necessarily solve that problem. So, I don't think it's a stretch to say that whatever behavior we want a machine to do, so long as that behavior is rational, we can write down an optimization problem that describes what we want. The challenge usually is in solving that optimization problem, or very closely related to that, formulating it in a way that is amenable to being solved. So if I want a robot that, if I'm a company and I'm manufacturing a home robot that is going to clean people's homes, I could write down an objective that says maximize the profit that my company makes. Now that is a well-defined optimization problem. The robots will act in a way so as to maximize profit. The problem with that, of course, is that that optimization problem is intractable. The robots have no idea what they should be doing to maximize the profit my company will make next year or something. So we need to formulate problems that are a little more tractable and design algorithms that can solve them. So I think that reinforcement learning, the problem statement, probably is enough simply because it's so general. But that's not a big accomplishment because it's easy enough to design a problem statement that's so general as to be unsolvable.
Right. So when it comes to designing the robots at maybe open-ended environment, or as you try to do, what it could be still we have to push for, or maybe the area do you believe that's what we have to maybe focus on or give much more attention? I don't know. How do you see that area?
Yeah, that's a good question. So I think that one aspect of robotics that, in my opinion, doesn't get enough attention, but it's something that we've been focusing a little bit on, but I think it's something that needs a lot more work, is the question of fully autonomous learning. And this might seem like a silly thing to say, like, well, learning, of course, it's autonomous. But the fact is that right now, it takes quite a bit of human effort to have learning algorithms actually run on real robots. Things like setting up the environment so that the robot can try a skill multiple times, instrumenting the environment to define reward functions, objective functions, things like that, providing demonstrations if that's what we're going to be doing. Imagine a future where you buy a robot. Maybe it's going to be a robot in your home whose job will be to, clean your bathroom. And you turn on that robot, and initially it has some kind of prior, it knows roughly what to do, but it doesn't really perform successful tasks in your particular home. But then after a few days, it gets better and better at that, right? Okay, we need the learning algorithms, but we also need the machinery so that when it messes something up, it can go back in and put things back the way they were, try again, things like that, and do that without you having to do a lot of work. So that degree of autonomy, the physical aspects of it, resetting the environment to try again, figuring out whether you succeeded or not, all those things, it's tempting to view them as kind of the engineering and infrastructure that goes around a learning algorithm. But when we really get down into it, it turns out there are a lot of really deep scientific questions there. As an example, one of the things that we explored recently is this question of whether multitask learning can be more autonomous than single-task learning. Now, this might at first seem like a strange idea because, well, multitask learning ought to be just harder than single-task learning. If you want a robot to learn many things, that ought to be much more difficult than having to learn to do one thing. But if those many things are somehow interconnected with each other, you can learn those many things together more autonomously than you could learn a single thing. So if you're learning to make a cup of coffee, well, you have a skill to put the coffee cup into the coffee machine and push the button. But maybe you spill the coffee. Well, if you have another task that you're learning, which is to clean up the spill, now you can use that as an opportunity to practice that other skill. So if you have enough skills such that they link up into a closed group, then you can learn all of them automatically without having to have people come in there and fix things up. So it turns out that we can actually make the problem harder, seemingly, but at the same time make it more autonomous. So I think exploring those kinds of questions is actually really interesting, and it may be one of the big bottlenecks on the way to fully autonomous learning-based systems, because we know from our past experience in the world of supervised machine learning, things like computer vision, speech, NLP, that if we get large amounts of data and high-capacity models, these things tend to work really well. The big obstacle to having large amounts of data and high-capacity models in robotics is that these robotic experiments are extremely onerous. They take a lot of human effort. So if they can be fully automated, if basically the robot can work harder than the human does, then we can leverage the benefits of large data sets and high-capacity models in robotics.
Great. So when it comes to strategies you think may be rich, or maybe you think maybe it's more reliable. For example, you speak about the offline reinforcement learning versus online one, or maybe model-based or model-free. If you can tell more about maybe the trade-off that you believe that it's okay to have this trade-off and it still have the reliable result. I don't know if you can elaborate more about that.
Yeah. So for me, one of the big, I would say, kind of overriding considerations in building effective robotic learning systems is that they need to be able to utilize large and diverse sources of data. We know this is critical for learning-based systems to get generalization and robustness. And people have spent a very long time studying how learned models in low data regimes can be effective and robust, and it is extremely hard. Whereas when you have a large data regime, which is basically the norm now in all supervised learning systems, it seems to be a lot more straightforward. So that means that if we want robotic learning systems to work, they need to be able to train on large and diverse sources of data. In reinforcement learning, the only way I can see to do that right now is with offline reinforcement learning algorithms. Now, offline reinforcement learning doesn't mean that we're going to exclusively use offline data. Rather, it means that we're going to have methods that are capable of utilizing large amounts of offline data. Now, in practice, in order to fully perfect behavioral skills, these robots might actually go out and perform some amount of additional online training in a very particular narrow environment to really perfect their behavior. But their robustness and generalization is going to come from large amounts of diverse offline data. Because collecting large amounts of diverse data online means like repeatedly revisiting all those different diverse settings, and I think that's going to be extremely difficult.
Mm-hmm. Right. So when it comes to resilience or redundancy, maybe in the design of the network or maybe the robot itself, how do you see the concept of resilience or redundancy in the design of the network? Do you think it's sufficient, or do you think we have to look for something beyond the structure we have already?
Yeah. That's a very difficult problem. So, in my group, we've been doing some work also in domains that where such things are critical, domains like autonomous flight, autonomous driving. We don't have a solution yet, but my hunch is that longer term, we'll find that the methods that are the most resilient and the most robust are the methods that effectively use learning and generalize effectively. It's very tempting to think about resilience and robustness as the problem of imposing hand-designed constraints on learning-based systems. I don't think that approach is going to work because I don't think we're smart enough to come up with the right constraints, especially when we have a learning-enabled system that has to deal with rich and complex sensory perception. So it may be possible to write down a constraint in terms of well-defined predicates, like I don't want my autonomous car to get within 50 centimeters of a human pedestrian. The problem is that the autonomous car has to operate on sensory inputs, and I can't define a constraint like that in terms of LiDAR point clouds or camera pixels. So that means that somewhere in there's going to be a learning-based system mediating this whole interaction, and the hand-designed constraints are not going to apply to the lowest level of the embodiment. So that means we can't rely on hand-designed constraints. We have to rely on learning systems that are robust to distributional shift, that generalize effectively, and we need better theory to understand the behavior of these learning-based systems. But I don't think we're going to solve the problem by shoehorning kind of constrained optimization methods from other areas that make strong assumptions about knowledge of the state. I do think there's more we could do, however, and I think that the solutions will come from those fields of machine learning that study robustness, resilience, and adaptation, and that is a very active area of research. Things like distributionally robust optimization, models that adapt at test time to distribution shift, domain adaptation, things like that. And I do think that those areas are very much worth pursuing, and they will eventually contribute to more resilient autonomous robots.
Before going to the audience question, I have one question. Do you have any experiences in your work, counterintuitive result? Because sometimes we believe, maybe it's been to the model simulation, sometimes we get certain result, but when we deploy it, sometimes it's counterintuitive, and there's something, I don't know if you have something like that.
Yeah. I mean, yes, that happens all the time, and certainly our best ideas often don't survive first contact with the robot. But I'm trying to think of a good example in this case. One pretty intriguing result that we actually that we figured out recently. This is actually not something we've even released yet, but we'll probably release the paper in a few days. Is we've been thinking a lot about how generalization in reinforcement learning compares to generalization in supervised learning. And there have been a number of papers over the last few years that showed kind of somewhat anecdotally experimental results that suggest maybe generalization is kind of harder in RL in some way than it is in supervised learning, but no one really had an explanation as to why. And also, they're very difficult to compare because they're just different problem statements. So my thinking on this topic was always that, well, maybe there's kind of nothing there. Like, generalization is what you get from lots of data, so just don't worry about it. Train your RL system on more experience and it'll all be fine. But we actually figured out recently, and this is some more theoretical work that we'll hopefully release in a few weeks, that there's actually fundamental reasons to believe that generalization in RL is harder than generalization in supervised learning, because RL systems need to address epistemic uncertainty differently. Essentially, briefly, the problem comes down to the fact that in a supervised learning system, if you do well on the training set and you don't overfit, then you will do well on test points from the same distribution. In reinforcement learning, we can formulate a similar kind of assumption. Let's say you have a robot that learns to grasp 100 different objects, and now it's going to try to generalize to new objects. It turns out that you can set up these reinforcement learning problems in a way that you can do arbitrarily well in the training set, not overfit, and still do arbitrarily poorly on the test set. And we can actually prove this in theory, that this problem exists, and in practice we actually see it showing up. And to me that was very surprising, because I always thought, well, it's just statistics, like you have your training set, you have your test set, how's the RL problem different? But it turns out it is different. And deep down, the reason it's different is because in RL, your payoff is much more complex. So in RL, you can mess up in different ways that have different costs, and therefore you need to place a different value in your epistemic uncertainty. So we'll release this work in a few weeks, but to me this was a pretty surprising result, because I always thought, well, we don't need to worry about this stuff in RL any more so than we worry about it in supervised learning, and it turns out that's not the case.
Appreciate that. So again, there's a question. There's a question from Samuel. I asked it, in 2017, Alex Erpin from Google wrote a blog post called Deep Reinforcement Learning Doesn't Work Yet. And this post showed the multiple weakness of the field, claiming that it's a difficult field to deal with and for now. And it's promising, but nothing more than that. In general, I would like to hear your opinion about whether you think DRL works now in 2021, and whether he is optimistic about it.
Well, it certainly works now. I mean, X, the Google X, the Alphabet company, they're building a product around DeepRL that's already a public thing. It's called the Everyday Robot Project. So it works well enough for a giant, multi-billion-dollar company to build a product around it. But maybe the more nuanced answer I would give is this: that I don't think DeepRL is any different from any other technology in this regard. There's always a kind of a maturation process. So if we rewind back to 2008, we would say, well, deep learning doesn't work, right? Deep learning is this funny thing that some people at the University of Toronto do to train classifiers on MNIST digits. But skip forward a few years, and all of a sudden deep learning is taking over the field of computer vision to the point where just a few years after that, it would be impossible to publish a paper in CVPR if it doesn't have deep networks in it. So any technology has to go through a process of maturation, and during that process, a few things happen. Of course, we develop a better understanding, we develop better theory, we develop better algorithms, but the other thing that we develop is better workflows, better engineering standards and practices that make seemingly brittle and fiddly technologies much more reliable to use. And I think this could be said for pretty much any technology. Any technology at one point was something that required a lot of guesswork and a lot of fiddling, until we fiddled enough to the point where we understand the parameters under which things work, and then it seems like it's reliable. So, we could say that, any any reasonably competent programmer could, download PyTorch or TensorFlow and get a ConvNet up and running within some fairly limited amount of time. But that's because the standard packages already have a lot of those delicate decisions kind of made in a reasonable way. It's not like we've figured out some really, really deep, profound truths there that we didn't know in like 2008 or 2009. We've just got a few of the details right to the point where we don't have to worry about them as much. And I think the same thing will happen in DeepRL. And I don't think it's going to be some sort of like, tectonic shift where all of a sudden just everything clicks. I think it's just going to be the same thing as in any other field of science, gradual progress until things are much more mature.
I have questions for Mark. Can you give your opinion about multi-agent reinforcement learning?
I don't think I have a particularly sophisticated opinion in regard to it. I mean, there are domains where multi-agent reinforcement learning is important because we want to control multiple agents. I mean, there's certainly deep and unique algorithmic questions, a lot of them centered around the fact that we have to do decentralized decision making and have some sort of consensus process. I think there are also a lot of questions that are shared in common with all other kinds of deep reinforcement learning, how to design algorithms that are more efficient, more stable, and more reliable, and probably those advances are going to facilitate more effective multi-agent learning as well.
I have a question also from Ivan. Ask us about, with soft robots, there are so many sensors, touch, for example, and so many actuators, more than few joints. How do you imagine if something like that could be controlled by training? For example, random acceleration will just produce poor policies, and no amount of simulation will give you a remotely good trajectory, as it seems.
Yeah, that's a great question. I think that's actually one of the strengths of learning-based methods. So it's, there's a spectrum of problems from problems that are easy to characterize to problems that are hard to characterize. So free space motion of a rigid robot is, it's impossible to beat a good model-based controller for that. Like, you can do reinforcement learning can control a rigid robot in free space, but it's kind of pointless. Like, you're not going to do any better. On the other extreme, we get to really messy things where, like you said, there's a mess of different sensors that we haven't characterized or calibrated properly. There are actuators that have complex nonlinear effects. There's deformation, etc. And in those settings, I think learning is going to do great because to the learning algorithm, that problem looks exactly the same as the problem with the rigid robot in free space, whereas to a model-based algorithm, it looks completely different. So the big power of these learning-based methods is that they make significantly fewer assumptions, and therefore the same method that works on the well-characterized system is likely to work exactly the same way on the poorly characterized system. We've experimented a bit with reinforcement learning algorithms for soft robots. A few years ago, my student Abhishek Gupta had a collaboration with Clemens Eppner, who was at the time a student at TU Berlin, where Clemens brought his soft hand that he developed with Professor Oliver Brock at TU Berlin, and then him and Abhishek figured out how to control it with reinforcement learning. Abhishek applied an algorithm that he had previously developed for the PR2 robot, which is a rigid robot, but it basically worked on the deformable hand. It was a pneumatic-driven hand, pretty much the same way. So I think that I'm actually very optimistic about the promise of learning-based methods, particularly in those settings where you have weird and messy actuators and sensors. And I think it's also a really powerful tool potentially for prototyping actuators and sensors, because if you have a very general learning algorithm that you can throw at whatever robot you design, you don't have to worry so much about control. You just mess with your hardware, then run the RL algorithm on it and see what it does. And I think that's actually potentially a really promising technology.
That's a good point, yeah. And the last question from John, he asks us, many researchers, Andy Jones and John Silliman Winter, have written a blog post on common practices to debug deep reinforcement learning, which is a difficult matter. It would be great if you could give more tips based on your solo expertise.
Yeah, that's a good question. I mean, to sort of describe this briefly, I think a lot of these are going to sound exactly the same as the tips we would give for any other kind of machine learning problem. But, usually the way that we go about addressing kind of a big robotic learning problem in my group is we first set up a small problem, a medium problem, and then a big problem. So the small problem should be basically something that verifies the correctness of your implementation. The medium problem is something that has the qualitative properties of the final problem you want to solve, but is in simulation, efficient and fast to run and easy to prototype with. And then the big final problem is the one that you actually want to solve. So the big final problem might be you actually run a real physical robotic system to do like real world training. The medium problem is something simulated that is not necessarily high fidelity, but has many of the same challenges as the real thing. And then the small problem is basically like a unit test to make sure you coded up your algorithm correctly. So you first get the small problem to work that basically verifies your implementation is correct. Then you get the medium problem to work because you can iterate quickly, and that one verifies that your implementation can actually solve the problem you want to solve. And then you get it working on the real hardware. And that kind of pipeline seems to work pretty well. I think, looking forward a little bit more, I would say that workflows in general are one of the things that we don't pay enough attention to in the formal kind of academic study of reinforcement learning. And I do think that we need more effort around defining effective workflows that are not just what I just said, not just sort of community lore, but actual formalized practice. So as an example, in supervised learning, we almost don't think about this, but the training validation set split is a workflow. It's something that somebody came up with. There's statistics behind it that say that it's like valid, and it's been the workhorse of supervised learning research and supervised learning practice for the longest time. Like without it, it would be unthinkable how to get a supervised learning system off the ground. So what's the equivalent for that in reinforcement learning? What's the equivalent for that in robotic learning? We have some ideas, some ad hoc heuristics, but I think we need a bit more research to formalize that, and that would actually go a long way towards making these tools broadly applicable.
Right. So I'm curious about that simulation to reality gap. What still maybe something you believe still maybe hard maybe to capture in simulation? Maybe you think that to achieve high fidelity simulation or to have the same exact performance we expect when it comes to deploying robots in reality. So I don't know what could be aspect you believe is still missing or we have to consider.
People. Can't simulate people very well because simulating people is just as hard as creating intelligent machines. But maybe more seriously, I know a lot of folks who work on simulation, who build simulators for a living. Actually, when I was an undergraduate, I spent a little bit of time working in a lab with Professor Ron Fedko, who works on physics simulation, and they can simulate a lot of different physical phenomena very realistically. These are the kind of simulators that are used for film, for high quality engineering applications. It's possible to simulate a lot of stuff if we're willing to put a bit of human effort behind it and get things set up properly. So with the exception of things like human brains, I don't doubt our ability to build high fidelity simulators. However, it's perhaps instructive to think about why is it that in other areas where machine learning has been successful, areas like computer vision, speech recognition, things like that, simulation is usually not the go-to tool. We could try to solve computer vision problems by using state-of-the-art graphics tools, generate lots of images, and build perception systems that way. And people have tried to do that. But across the board, the most successful perception systems that are actually used in production are not built that way. They're built using real data. It's not just because the simulation is not realistic. A lot of it is honestly because the real data is just easier. It's easier to use, it's easier to get, and it's more representative of the real world. And I think that it's partly a quirk of our current technology that this convenience doesn't seem to play out quite that way in reinforcement learning and control, but I think it'll get there. And I think technologies like offline reinforcement learning will help get us there. So I think that if we really put our minds to it, I don't doubt that folks who work on simulation professionally can simulate just about everything short of the human brain. What I think is that it's just going to be more convenient not to, in many cases.
So I think one of aspect also in machine learning community, and I think in academia in general, that's point about reproducible result. And there's a lot of discussion going on most often today about the reproducibility and publication. And how do you see you can manage that? I don't know, how do you see this problem from your perspective in your field, or maybe also in general about reproducibility in the results?
Yeah, that's a good question. So I think robotics especially has always had a lot of difficulty with it, because in robotics we end up with these custom-built, hand-designed systems oftentimes the particular laboratory setup I have is not the same as the one you have. I have a particular piece of sticky tape on the gripper of my robot that makes it work a lot better than someone else's, or things like that. So it is an issue. I think in robotics especially, another big part of that issue, honestly, has been cost. So part of why it's difficult to standardize around reproducible systems, and part of why everyone has different hardware, is because hardware is expensive. So if I bought my awesome robot 5 years ago and I spent a great deal of money on it, I'm not going to just go and buy another one simply so that I can reproduce someone else's algorithm. But I think these problems are solvable. I think increasingly the cost of high-end robots is going down, but also the need for high-end robots is going down. So as we get algorithms that are more capable of controlling imprecise, low precision, and low cost robotic systems, it'll be easier for me to say, hey, I want to run your algorithm. I'll just get the same robot that you had. It's a few $100s. Yeah, let's just get it for the sake of reproducing that. That's much easier to do than when the robot costs $200,000. The other thing, and this is maybe a little bit more far-fetched, that I think is potentially a promising thing, is to think about robotic systems that are not directly owned and controlled by individual researchers, but that are a centralized resource, much like compute servers. So I think the technology is not there yet, but I think we could imagine at some point in the future where we could have robots that are located in at some facility, just like compute servers are located in a server farm, and you can log in and run stuff on the robot, and then different people can try running their thing on the same robot or across different kinds of robots and things like that. And we've seen some early efforts in this direction. For example, there was an effort out of Georgia Tech, I believe it was called the Robotarium. There was an effort from Stefan Tillix's group at Brown called the Million Objects Challenge that all started to get at this point a little bit, and I think we'll see more of that, and that's potentially really promising on a longer timeline.
Right. So I'm curious about maybe the biggest technological blocks do you believe that still we have when it comes to robotics? Maybe what would be technological blocks do you believe we have?
You mean for applications, or?
Yeah, maybe in what we develop, maybe still if you have crazy idea. I don't know what kind of thought you have, or capabilities you believe the robot should have, maybe, and you still believe that's a technological block, maybe in terms of technology and also application as well.
Yeah. Well, I think that a lot of the big roadblocks really come down to generalization, come down to the ability of the system to do something not just in one setting, not just in one environment or with one set of objects, but in any setting that it might find itself in the real world. And in a sense, if we imagine why, for example, the development of autonomous vehicles has proven to be such a long journey, a lot of it really does come down to the fact that autonomous vehicles, in contrast to robots that are situated in more controlled environments, can find themselves in all sorts of weird situations. And once we have robotic manipulators in open world environments, the same issue will start to come up. So I think to a large extent, kind of the radius of deployment, with the center point being at the factory and the far off point being in your home, that how far that robot can go will be determined by its ability to generalize. And that's a big part of why I think machine learning technologies are one of the most promising ways forward for robotics, because it most directly addresses exactly this question, the question of generalization.
Mm-hmm. Right. So since it wasn't a few questions, I don't know if you have any ideas or aspiration when it comes to what we have in the community. I don't know what kind of thoughts do you have when you think about what you want to achieve in coming years. I don't know if we have any kind of thought.
In the robotics research community?
Yeah.
Well, I think that one thing that we ought to do more of as a robotics research community is share more things. And this comes back to also a little bit to the point about reproducibility, but it's not just about reproducibility. A really ideal future for me is one where if another researcher at a different university wants to run a robotics experiment, they don't start off by cooking up some kind of custom-built robot system running a bunch of experiments with it, collecting training data and doing something like that. They start off loading up, robot data set for kitchen tasks or something, initialize their system from that, and then run their experiment. And that kind of standardization has been extremely successful in other fields. For example, computer vision has prospered tremendously from having standardization, not just in terms of evaluation, but in terms of kind of a starting point, something that someone could load up and immediately get a system with some basic level of competence and then build from there. And that's something that's been very hard to get in robotics. We actually had an early effort in this direction that was almost kind of a trial run of what it's like to collect a data set across multiple different research labs. This was called RoboNet. We released it about 2 years ago with, it was a data set of manipulation data collected by researchers at UC Berkeley, Stanford, Carnegie Mellon, and University of Pennsylvania. Now, it was a trial run. It ended up being not that useful, partly because just the behaviors that we had in the data set were not that interesting. But it was an interesting experience in the sense that it taught us a lot about how to gather data from multiple sources and format it in ways that could be used by different researchers in different places. And I think we ought to be doing a lot more of that.
Mm-hmm. This is a good point, yeah. But I'm curious to ask you, as we know research is so challenging, I don't know, do you have any moments, maybe sometimes, I don't doubt this moment when you research or the direction you're going for, how you overcome this kind of feeling, if you have, I don't know, how do you encounter these feelings, yeah?
That's a good question, yeah. I mean, the answer is yes, of course. And I think any scientist who is working on ambitious problems is, if they're realistic with themselves, they're going to have some doubts as to whether this is all going to work out or if it's all a dead end. Something I would say, and this is particularly maybe a bit of advice for students who are getting started, for junior researchers who are thinking what the heck am I going to do in this field? I think it's important to have big goals and dreams and so on, but to also learn how to derive satisfaction from working on the right problem, even if it's a little hard to tell whether you're making progress on that problem. The reality of science is that most people working on tough scientific problems are not going to be the ones that make the big progress there. But if lots of people don't work on those problems, then nobody's going to make progress. So it might sound a little bit dark, but lots of people have to fail so that the field as a whole succeeds. And I think we as a community need to be kind of cognizant of that and celebrate not just the fact that someone got something right, but also that lots of other people tried and got it wrong. Because if lots of people didn't try, then probably no one would have gotten it right. So a lot of it has to do with learning how to derive satisfaction from the process. And the satisfaction of knowing that you're working on important problems that are advancing the field, even if you yourself are not individually meeting with the kind of success that you had hoped for, in a given year or month or whatever.
Mm-hmm. That's a very wise point. We have 3 questions left. First of all, do you think ego is important for you when you speak about ideas or maybe, I don't know, the community? Do you think ego is important for you?
I don't know. Not sure how to answer that question. I mean, I think to me the things that matter a lot is actually seeing stuff work. I'd like to see the robots actually work. I'd like to be the one to do it. If someone else does it, I'm pretty happy with that too, though. So I don't know. I think that science ultimately has to be a very cooperative community effort. I think there's a little bit of a myth, and maybe this part of this is human nature, around the hero scientist. There's one person who's just so smart and brilliant that they figure everything out. But that's not really how science works. And every time in history where there was one brilliant person who figured something out, if you dig a little bit deeper, it's actually because they were kind of in the right place in the right time, surrounded by lots of other people that basically gave them the pieces. So that's not to understate the accomplishments of very smart and capable individuals, but science has always been a social endeavor. Certainly it is today, but I think it also was that way in the past too. It's just that looking back on history, it tends to cast the success into much clearer focus and sort of blur away everything else. But that's not giving us a realistic picture. So we have to be comfortable with it being a social process and celebrate each other's successes.
a good point. Yeah. If there is a book inspired you have ever read, I don't know if you have a book you have ever read and was inspiring and stick to your mind.
I can give an answer, but it's going to sound a little bit naive. This is not really so much about robotics, although this is by an author who has written a lot about robotics. So, especially when I was younger, I was a big fan of the writings of Isaac Asimov. I think that's probably going to come as no surprise to lots of people listening to this. But actually, the stories from Asimov that I actually found the most inspiring were not the ones about the robots, although those are really cool too. It was the Foundation series, where a lot of the premise, a lot of the theme behind those books was Asimov's idea that, to kind of paraphrase, a sufficiently deep scientific understanding of how everything works can be used to make arbitrarily accurate predictions arbitrarily far into the future. Although, of course, a lot of the books then kind of turn this idea on its head and bring up, sort of unexpected, really weird events that just upend everything. But that really got me thinking. That I found that to be very inspiring, this idea that if we just understand the universe well enough, we can make these like amazing superhuman predictions and just like accomplish way more than an individual human mind could ever fathom. To me, that in many ways, that is also the promise of artificial intelligence. And I think also those books provide an interesting cautionary tale about how that idea can also go horribly wrong sometimes. So we kind of need both the good and the bad.
Nice. And what could be the most important quality you have to maintain as a researcher? What's important quality you believe you have to maintain?
Humility. Because because otherwise, if you don't maintain humility, then it will be imposed upon you by some very unfortunate failures. But also, I think there is a certain degree of kind of mental acrobatics that a scientist needs to do, because you have to be simultaneously very ambitious and also very comfortable with failure. Because you have to try big and ambitious things, but you have to also be okay with knowing that most of the time it's not going to succeed. So it's I think some people are very good at having that mindset. Some people are less good, and it takes it's unnatural, I think, for a person to have that mindset.
Yeah, that's really a good point. Yeah. Lastly, maybe what advice was given to you was life changing? I don't know if you received any advices, maybe the good ones that you believe was life changing for you.
I can give one answer, but it's not going to be. I'm afraid it's not going to be a particularly inspiring answer because it's a very nitty-gritty technical point. But it does stand out in my mind because in my own career, I think this very small, very technical bit of advice actually ended up making a big difference. So this is maybe not quite what your question is getting at, but I'll tell the story anyway. I think it's a neat story. So in 2015, I was a research scientist at Google, and I was working on robotic learning for grasping. So we had this idea that we wanted to develop a learning-based grasping system that could practice grasping lots and lots of different objects, and because it could learn autonomously, it would acquire these generalizable skills, and we could show that kind of you could actually have an RL system that generalizes broadly. And at the time, that was not something that had really existed. And we had a lot of trouble getting this thing to work. We set up all the robots, they were doing their thing, we were training models, but they just didn't work as well as we wanted. So it was myself, Peter Pastor, and Alex Krashevsky were working on this, where Peter was doing a lot of the kind of robotics setup, Alex was doing a lot of the convnets, and I was kind of trying to put the pieces together. And when things weren't working so well, I kept suggesting that, well, maybe we need to scale back and simplify. We just had gone to Costco and bought thousands of different objects, and it was a very difficult problem. So, let's just simplify. Let's pick up, colored blocks or something and at least get that right. And I remember every time I would suggest this, Alex would always tell me that, no, just hold on. The system is going to be exactly the same with a simplified setup as it is now. That's not going to make a difference. Just keep running and collect enough data. Go read the AlphaGo paper. They collected 10 billion games of Go. You only gave me a few 100,000 trials. Just keep going, be patient. And I remember thinking well, this guy, okay, Alex Krashevsky, he knows something about convnets, but he's not a roboticist. What does he know? But I listened to him, and I'm glad I did, because it turns out that if I had just, we just kind of kept kept going, didn't mess it up, and as he predicted, the thing eventually worked, right? Because the basic technology was essentially there. That taught me a valuable lesson, I think, in terms of sometimes you have to trust your instincts, and you also have to have an appreciation for the power of data-driven methods. But in my own career, that turned out to be a good decision. Listening to Alex, because in many ways the system that we built and the success of that system, was part of what enabled me to get the job that I have now and things like that. So that turned out to be career-wise very beneficial. But it's a very technical point.
That's a really good one. I think that's really good advice. I deeply appreciate hearing that. So I don't know if you have any final words you'd like to say for the audience listening to. If you have any final words you'd like to say.
Nothing in particular, except maybe something I would mention is that robotics research and robotic learning in particular, it's a very difficult field in the sense that it takes a lot of work and it takes a lot of interdisciplinary expertise. And something that I see oftentimes from students who get started in this area is that it's pretty easy to get discouraged because there's all this progress that can be made with machine learning technologies in other areas that seemingly comes at a lot less pain because there's like data sets already there, the models are already there. But I think it's also something that is going to be very rewarding for people who work on, for people who stick with it, because while machine learning, it's coming back to that point that you asked me about before regarding Alex Serpon's blog post, the maturity of the field. Like, the very thing that makes robotic learning less mature and harder to deal with is also the thing that makes it more promising as a research area, because this is where there's potentially a great deal of untapped potential. And students who are starting their PhDs maybe now, they're in a position where they could see these technologies really turn from academic exercises to things that are broadly used in the real world. So it's a more painful area to work in, but I think that that also will come with its rewards, perhaps very soon, perhaps in the span of somebody's PhD who's starting their degree right now.
Thanks so much, Serge. I think that was very inspiring and very insightful. I deeply appreciate your time. Thanks a lot. Thank you.
Thank you for having me.